Hey, good afternoon. Let's get started on our talk for diodes. So, yes, still chapter 1, diodes. Typically is the easiest way to remember 321 is 2 weeks of diodes, 2 weeks of transistors, 2 weeks of op amps, 2 weeks of logic circuits, 2 week of digital computers. 1/5. But give or take a few lectures here and there. Isn't there one in the lab kit? I think so. Why is all right? Ideal diode states, ideal diode model. Let's look at the offset diode model. So now the offset diode model is no different from the ideal diode, except that it requires a certain amount of voltage in order for the diode to turn on. Ideal diode, of course, they are not real, simply hypothetical. So offset diode model is simply an ideal diode in series with the turn on voltage. Now, if you turn on voltage with a silicon diode, 0.6 or 0.7, for germanium, it would be 0.2 or 0.3. The actual value does not matter. It depends if it's a, whatever the model is, it would be either stated in the problem or you can make an assumption. Okay. That simply is the voltage that is required for the diode to turn on. The diode turn on voltage. Okay. Circuits can be analyzed in the exact same manner. So typically what I would do is I would simply analyze the circuit with a ideal diode model, either on or off. And then I would deduct 0.6 or 0.7 volts for every diode that needs to be on. Okay. And so the offset diode model is nothing but the ideal diode model with the diode turn on voltage. All right, then let's take a look at the Shockley equation. This is also known as the diode equation. Okay, diode equation. It is one of the most important equations that we use for modeling our devices, and we'll encounter it again for transistors also. All right, so let's break it down. We have the diode current and the diode voltage. So ID as a function of VD, and we're already familiar with the diode characteristic, right? So what do we need to describe the relationship between the diode current and the diode voltage? Well, 4 parameters, 1, 2, and 3. And then, of course, VT is KT over Q, hence 4 parameters. All right, let's take a look at IS first. IS is the saturation current. What does it mean? Typically, the saturation current refers to the reverse saturation current. And arises from the fact that there are minority charge carriers in a PN junction or a PN type semiconductor, and they move in response to the applied electric field. Okay. So in a p-type material, electrons are the minority carriers. In an n-type material, holes are the minority carriers. So if you have a p-n junction diode and you apply negative to the p-type end and you apply positive potential to the n-type end, the diode is now reverse bias. It's reverse bias, the junction, the depletion region is increasing in size. Majority carriers are pulled away from the junction, right? P, n-type material, negative, positive. Here you have holes as the minority carrier. Here you have electrons as the minority carrier. Okay. So the majority carriers are pulled away from the junction, so the depletion region increases. But the minority carriers on both sides are repelled by the external voltage, so they are moving towards each other in the junction. So a current starts flowing because of these minority carriers. And that current is very small in value because the numbers of minority carriers are very small. Okay, so this is typically on the order of 10 raised to minus 9 to 10 raised to minus 15 amps. Nanoamps, picoamps, and femtoamps, very, very small. Okay, and it is a result of the fabrication process. And of course, the material properties, not just the fabrication process, also the material properties. Okay. So saturation current is typically very small. So that's the first quantity, the most important one. Then N, and we typically almost disregard N because N is a constant provided by the manufacturer. It's typically between 1 and 2 or just 1 and 2 or 1 or 2. Okay. It describes the non-ideality of the diode characteristic. For the most part, we simply take the value of N as 1. Hence, we tend to ignore it for many equations. So IS times E raised to VD over NVT, E exponent. Lastly, let's take VT. VT is the thermal voltage, and it also is typically used as a constant in many of these equations. The thermal voltage arises due to the temperature differences between two semiconductor materials. Okay, and it's given by KT over Q, where K is the Boltzmann's constant, Q is 1 unit charge, T is the temperature in Kelvin. Okay, temperature in Kelvin. At 300 Kelvin, just typically room temperature, the value can be calculated as 25.8 millivolts. Depending on the author, you might also see 25.9. But again, you can calculate this easily. If you take Boltzmann's constant in the units of electron volts, which is 8.6 times 10 raised to minus 5, you simply multiply it with the temperature, and you can calculate the thermal voltage at any given temperature. Okay, that's the thermal voltage, and that's it. That's the equation. Either VD or ID would be known to us, and you can calculate the other quantity. Right? If you say, okay, diode voltage is 2 volts at 300 Kelvin, what would be the diode current? Simply plug into the equation and solve. Because all quantities are known except for one unknown. And that's it. Okay. Make sense? Any questions? All right. So then let's get into the main purpose of this course, circuits. We're going to create multiple circuits using these devices, right? So the first few circuits we look at for diodes are rectifier circuits. Rectifiers basically convert AC to DC. And then there are inverter circuits. Inverters convert DC to AC. Okay. All right, before we do that, just want to do a brief recap on all the terms. For an AC waveform, what does VP stand for? What does the P stand for? Okay, simply peak. Yes, it's true. I heard somebody on the speaker. So that P stands for peak. And P dash P is peak to peak, meaning it's 2 times peak. It also applies to current, IP and IP dash P. Then P can also be referred to as M. And M is for magnitude. Magnitude, or even sometimes referred to as the amplitude. Essentially, it describes the waveform in the y direction. It's the size of the quantity in the y direction. X-axis is always time, either in seconds or in radians. Right? 1 unit circle is 2 pi, 360 degrees. 1/2 cycle is pi, or 180 degrees. So y-axis is the size of the waveform. So 1 peak. What is RMS? VRMS. Root means square. What does it mean? 4 divided by square root of 2 for which waveform? Well, AC waveforms, yes. Okay, so brief recap from 201. We say that the waveform is symmetrical, right? Around the x-axis. Half of it is above, half of it is below. If we go from 0 to a positive value, then come back to 0, go to a negative value, and come back to 0, we say that is 1 full cycle, right? The vector moves from 0 degrees in a counterclockwise fashion, comes 1 full cycle or 1 full circle, 360 degrees. Half a cycle is pi, 1 full circle is 2 pi. Symmetrical around the x-axis, half above and half below. What is the average value of the waveform? It's 0, right? So typical AC waveforms, if they're symmetrical around the x-axis, would be equal to 0. Yet, if you apply an AC voltage to a resistor, energy is being transferred. Resistor will get hot because it is dissipating thermal energy. So how can we mathematically describe the average value of the waveform? So faced with this, the early scientists and researchers decided that instead of taking the average of the waveform, we will first square the waveform. So if it's V of t, let's square the waveform. Then we will average out the waveform. So the average of the waveform would be you integrate it for one time period, 0 to t, divided by the number of samples, 1 over t. And because we squared the waveform at the first step, at the end, we will take a square root. And so it literally is the square root of the average of the square of the waveform. Root means square. Literally is the root of the mean of the square of the waveform. When you perform this analysis, when you perform this calculation for a sinusoidal waveform, it turns out that the relation between the two VRMS 1 over root 2 times VP. But it is only true of sinusoidal waveforms. For other waveforms, you have to perform that calculation. The triangular, square, sawtooth, any other kind of waveform, you perform that calculation. Okay, so that's VRMS. Okay. All right, let's look at the first circuit. Actually, not first circuit. Let's do a broad overview of what diode rectifiers are. Okay. The most common and popular application for a diode, the regular diode, is in a rectifier circuit. Okay, rectifier circuits are basically AC to DC converters. Transformer is an AC to AC converter. Okay, transformer. So let's go on a brief tangent. We studied inductors in 201, right? Capacitors and inductors are energy storage devices. Capacitors store energy in the form in an electric field. Inductors store energy in a magnetic field. So if you take two inductors, both of them have their own magnetic fields. If you bring them in close proximity, the magnetic fields interlink, they cross-link, and energy from one is transferred to the other. Okay, that is the operating principle of a transformer. A transformer is basically two inductors in close proximity wound around each other. There's a core, right? Inductors have a core. So if you have the same core shared between two inductors, then they are wound around each other. The magnetic fields are interlinked, and the energy from one is transferred to the other. That is the operating principle of a transformer. Transformers are great devices because they are used to either step up the voltage or step down the voltage. So transformer has a primary coil and it has a secondary coil. And the primary coil is so called because the input is applied to the primary coil, output is taken from the secondary coil. So depending on the turns, the number of turns in the inductor, you have something called as a turns ratio. Turns ratio. That's basically the number of spiral coils that are present in that inductor. And depending on the number of turns, the voltage at the secondary side of the transformer is either higher than the input or lower than the input. Okay. In a power generation facility, when there's a power plant, it generates voltage. You need to send this voltage over long distances, long distance transmission lines. The voltage is stepped up. The reason the voltage is stepped up is because we want to keep the current low. So we increase the voltage. It is sent over very long distances. As it gets near the city, the voltage is now stepped down. If you go down any residential neighborhood, next time take a look at the light poles, the electric poles that are distributing the electricity. Every so often, you will see rectangular, not rectangulars, round cylinders mounted on top of the light pole. Those cylinders are transformers and will have multiple outputs coming from the transformer because it is taking the high voltage transmission line and is stepping down the voltage. That voltage is now 110 volts or 220 volts that is going into each residential neighborhood. Okay, the same principle applies here. Every single adapter that we use for our consumer devices has a transformer inside it. Whether you plug a television into the wall or a DVD player, a desktop computer, a mobile phone charger, your tablet charger, they all have they all have rectifier circuits and transformers inside it. Plugs into the wall outlet. That wall outlet has 110 volts. That is stepped down. So step down to our desired value. Let's say 10 volts. Okay, 10 volts. And the 10 volts goes through a rectifier circuit. maybe comes out at like 8 volts and goes through a filter capacitor and a regulator. And then finally, our desired output of 5 volts goes to the load. Okay, that is the circuit that is present inside every single AC to DC converter. All of power generation, I would say almost all of power generation and distribution is in AC, whereas most of the power consumption, at least with regular, residential customers or consumers, is in DC. Okay, everything's DC. Our devices, whether it's tablets, laptops, desktop computers, monitors, television, any electronic device that you use nowadays, not nowadays, been for a long time, it's always been DC. There is a AC to DC converter inside every device. If you have looked at the back of a desktop tower, you would see a small rectangular device with a fan. That is a AC to DC power supply. Okay. 25 years ago, one of the earliest laptops I saw, never used it myself, never purchased myself, but I was using it for a while as a graduate student. It had a power supply built in, meaning it didn't require an adapter. You simply plugged it into the wall. Okay, just an example. But again, everything that we use is DC, so it incorporates a power supply circuit like this inside it. Now, in the old days, we used to have these transformers that would be about this big in size. And so if you've ever seen a older power supply, it will be far heavier than what you use nowadays. Nowadays, you have these mobile chargers. They are high, they have the exact same principles, but they have high frequency transformers. So we are able to squeeze down the size, small size, but the operating principle is still the same. Okay. All right. So I said that 133. Oh, one other, just a slight tangent and an example. How many of you have wireless charging devices? Mobiles, mobile phones, tablets, right? Several of you. So on the back of your device, whether it's a smartphone or a tablet, is an inductor. It's an inductive coil. And the wireless charging mat also has an inductor in there. You take your wireless charging mat and you plug it into the wall. Wall outlet comes into the wireless charging mat, gets converted to DC, and it's then sent to, actually not DC. It'll still be AC, but it's stepped down. And the inductive coil in the base mat has a magnetic field. Then you take your smartphone, which also has a an inductive coil in its back, and you place it down on top of your wireless charger. Now, the magnetic field from your smart device is linked with the magnetic field of your charging base plate. When the magnetic fields are interlinked, energy from the wireless charging mat goes into your smart device. And that's how it works. So if you have a metallic case on your smart device, it's going to short circuit that field, and the charging is not going to work. Or if it's very thick, it's physically going to protect your device, but electrically it might interfere because now your device is away and the magnetic fields are not able to interlink. That's all of this technology, by the way, is attributed. I mean, there are multiple researchers who work on different parts, but much of this technology was invented, or a lot of the research was done on by Nikola Tesla. So Tesla is attributed with the invention of the electric motor, the DC and AC motors, wireless charging, the Tesla coil. He had some fantastic ideas that he was trying to work on at the time of his death. One of the things that he wanted to work on was wireless power transmission, meaning you'd have electrical pole that would wirelessly send out electrical power, meaning you would not actually need to plug anything into the wall. Your device is just here, and it's receiving power and it's getting charged. So some good ideas he had. Many of them are now in existence. Some of them are just theoretical. Anyway, coming back to our circuits, let's look at the first rectifier circuit. That is the half wave rectifier. And what I'm going to do is I will use the ideal diode model to analyze this half wave rectifier. Right, let's look at the positive half cycle. This is the input right here on the left. And this is the output waveform. Okay, so we have in the positive half cycle, we can represent our input source as a battery with plus at the top. So is my diode forward bias or reverse bias? Is it on or off? Anyone? Positive connected to the anode. So you're right, it's on. And so I have current flowing through my load resistor, which will cause a voltage drop across the load resistor with this polarity. And so VRL, let's say I'm using the ideal diode model. So VRL is going to follow V in, or the shape of V in. If V in is 0.1 volt, V out is 0.1. If V in is 1 volt, V out or VRL is 1 volt. So I would get the ideal diode output. Okay. In the negative half cycle, the exact opposite happens. Polarity is now reversed. Diode is reverse bias. No current flows through. Output is 0. Output is 0 volts. And that is shown right here. VRL is 0 volts. So again, ideal diode is a very good model to perform a quick analysis for any kind of diode circuit. Now, if I wanted to accurately predict what the output voltage would be, then I would plug in a different diode model. So in this case, if I plugged in an offset diode model, then it would need 0.7 volts to turn on. And so my output would be reduced by 0.7 volts. That is indicated there, 0.7 volts. Okay. Now, one full cycle is a positive half cycle followed by a negative half cycle. And since this rectifier circuit is only on or rectify only one half cycle, it is known as a half wave rectifier. Make sense? Right. So there are many limitations, of course, and those are corrected with the implementation of a full wave rectifier. Now, typical question would be asked is, how in the world is this a DC rectifier circuit? Isn't it still AC? And the answer is yes. I mean, without any other additional filtering elements, we can call this a AC waveform, or I like to call it as a pseudo DC waveform. Okay, it's still in the positive direction. It's not going negative, but essentially it is still a time varying voltage. So we can treat it both as an AC as well as a DC waveform. It's not a flat line. Okay, so the average DC value would be far less. If we think of the output as mountains of dirt and we flatten it out, this entire space has a value of 0 volts, the negative half cycle, right? So if you think of them as mountains of dirt and flatten it out, that entire empty space needs to be filled in. So the average value, average DC value of the waveform is far less. That makes sense, right? And so not a very practical use of a diode rectifier circuit. This is a full wave rectifier, which is far better. And this also is not very popular for the reason that it requires 2 separate supplies. Now, in real life, would not have been 2 separate supplies. It was 1 single transformer with a tap in the secondary coil. And so this would be known as a center tap. And I'm simply drawing the secondary coil, not the primary coil. Center tap transformer. I have a diode here, and a resistor in the middle. This would be RL. If you look, the ground line is right here, and that means RL is connected this way to the center tap. Okay. So let's see how this is going to work with the ideal diode model. In the positive half cycle, the center tap transformer is going to look like this, behave like this. Plus, minus, plus, minus. So if this is diode A, and this is diode B, is A on or off? Positive connected to anode. Anyone? It's on. Now there shouldn't be any hesitation. If positive is connected to the anode, it's on. If negative is connected to the anode, it's off. And again, positive and negative are relative. Positive means higher than the cathode. That's all it means. But in general, positive connected to the anode is on. Negative, it's off. So current flows through that resistor in this direction from right to left, which causes a voltage drop across that load resistor with a polarity of plus on the left, minus on the right. This with regards to the circuit diagram. Make sense? What happens in the negative direction? Well, in the negative direction. Now this changes. Diode A is now reverse bias, so it's off. And diode B is now forward bias, so it's on. Current flows through this direction. And current is flowing in the same directions for both positive and negative half cycles through RL. Hence, it causes a voltage drop polarity in the exact same direction. Plus on the left, minus on the right. So in both the positive and negative half cycles, each diode is behaving like a half wave rectifier and is responsible for half the cycle, or rectifying half the cycle. So the other half cycle is not being wasted, energy is not being wasted. It's more efficient. Does that make sense? Let's take a pause. Let me know if you have any questions. Any questions? Okay. I'm assuming everybody understood everything. Want to have a pop quiz? Well, let's not have a pop quiz, but how about explaining the full wave bridge rectifier? So the downsides of the center tap are obviously that you need a center tap transformer, right? So more additional expense. It's far cheaper to just use a regular transformer and add in 2 more diodes. And you can have a full wave bridge rectifier. So this type of configuration is known as the bridge configuration, where you have 4 diodes, actually 4 components connected in a diamond shape configuration. And so I will illustrate how you want to draw this circuit. You have 4 dots or 4 nodes connected in the diamond configuration. And what we want to do is we'll draw our diodes with 2 of them pointing up and 2 of them pointing down. So we'll take these 2 diodes right here pointing up, and these 2 diodes here pointing down. They should be in the same direction. And what this does is it gives us 4 nodes, 2 of which have 2 anodes connected, and the other opposite end, you have 2 cathodes connected. That is where the output is taken from. So on the left, you have 2 anodes. That gives you the negative end of the output. And the place where 2 cathodes meet gives you the positive end of the output. And the other 2 nodes, where an anode and cathode come together, is where you would supply the input. V in. This would be VRL, the output. Okay. So let's analyze this. Positive half cycle. What will happen positive half cycle? Which diodes are on and which are off? This is A, B, C, and D. Is A on or off? It's on. How about B? On. C, D? C, you already know. So I have, with my ideal diode model, circuit that looks like this. And current is flowing in this direction through RL from right to left. Causes a voltage drop with plus on the right and minus on the left. Okay. Yes. Here it is just shown out here. Yeah. So it's shown out here, but effectively, of course, this is connected here. The diagram I drew out with my hand just makes it easier to explain. And then so Wheatstone bridge is basically, again, a bridge configuration. But again, there we have 4 resistors. And you're taking the output. So the configuration is a bridge. The diamond shape configuration is a bridge configuration. Yeah. All right. So negative half cycle. Polarities are reversed. Now C and D are on and A and B are off. The result being the same. So A and B, and here it's C and D. And the current is now flowing in this direction. However, for RL, the current is flowing in the exact same direction, causing a voltage drop with a plus on the right and minus on the left. Once again, creating both half cycles going in the exact same positive direction through the load. So if our input was like this, our output would be a full wave rectified output. Okay. And this is by far the most popular configuration because diodes are cheap. And so instead of using expensive transformers, just use a regular transformer and create a bridge rectifier circuit with 4 diodes. You get full wave rectified output. All right, questions? If you have an old mobile charger lying around, you might want to take a hammer, crack it open, take a look inside. Like a actual charger, if you're an old one lying around that you're not using, or maybe gone bad or whatever, just crack it open, take a look at the circuit. There is a time. So from what I know is mobile chargers nowadays, instead of using a transformer first, they simply take 110 volts and rectify it directly. So directly goes into the diode. So you get like DC at the output. Then that DC is stepped down or converted into high frequency AC, like 400, 500, or 600 hertz compared to like 60 hertz. And so that high frequency signal, well, high frequency compared to the power outlet, then requires a much smaller transformer instead of a 110 volt transformer. The size of the transformer is now far reduced, very, very small. And so then that small transformer reduces the weight of your adapter. That's why those adapters are very lightweight. Previous adapters that were available about 15, 20 years ago, they were very heavy. I'm sure I have one lying around somewhere in the office. So I'll bring it in for next class. But again, if you have an old charger lying around that you're not using, that's it. You can just open it up and take a look inside. All right, we'll end class here today, and I will see you all on Tuesday. Friday quiz is open today. Unfortunately, with Pearson settings being what they are, when I set a time limit on the assignment, like 30 minutes, it does not allow me to have an extension for submission on Saturday. I don't know why. So I've sent an email to them asking for confirmation of the setting. So it's only open from 8 a.m. today to 11:59, midnight today. Okay, so get your submissions in. It shouldn't take longer than 10 to 15 minutes, but I've given you 30 minutes. We'll just ease into the first few weeks. Okay. Submission of the PDF is on Canvas. It's not on Pearson. So please keep that in mind. And then Monday is a holiday, so I will see you all on Tuesday.